In this lesson, we are going to look at average rate of change and instantaneous rate of change. Now, a rate of change you've actually been seeing for a long time, even since middle school. A rate of change is a measure of how quickly one quantity changes respect to another. So similar to slope, right? That was another word for it from grade 9, as well as constant of variation. And so we know already that algebraically, the average rate of change, which we're going to use AROC for short, so that's important to note and to know what that means, is simply the change in y over the change in x, right? Or y2 minus y1 over x2 minus x1. So hopefully you recognize that as your slope formula from grade 9, just written with function notation. So graphically, as you can see written here for the average rate of change, I've shown you that it's simply the slope, which is our y2 minus y1 over x2 minus x1. Okay, so we're looking at the slope between these 2 points right here. So this line right here, and we call this line the secant line, and the slope of the secant line is the average rate of change. So we're not going to focus too much on that graphically. We're going to more look at algebraically with our polynomial functions. So let's take a look at our first example. Okay, so a football is kicked into the air such that its height in meters after t seconds can be modeled by this equation. So just a simple quadratic in terms of the polynomial. And first thing we'll do is we'll determine the average rate of change in the first second. So please pay attention to how we write this. Of course, in the first second means from t equals 0 to t equals 1. And so our average rate of change, our AROC, is going to be h at 1 minus h at 0, right? That's y2 minus y1, thinking about the slope formula, over 1 minus 0, x2 minus x1, which in this case it's like t2 minus t1. Okay, so I'll give you a minute. You can pause the video. Please go ahead and calculate that. Keep things as exact as possible. So you always want to keep as many decimal points as possible until you get to the final answer. Okay, so some fairly simple math there. Hopefully that makes sense. And now we're going to focus on the conclusion, because the conclusion with this is the most important part of this. Okay, so we would say, therefore, in the first second, I want you to be really specific here. This means that the height is increasing at a rate of 9.1, and note the units are meters per second. Okay, so the terminology there, whether it's increasing or decreasing, is really important. And then, of course, the units. Okay, and so that's probably maybe one of the new things that we are going to focus on. Okay, so pause the video and see if you can do B all by yourself, including the sentence with the interpretation. Okay, so since there was only 2 decimal places here, it made sense to keep that. Okay, hopefully that math makes sense. And then in terms of our sentence here, okay, now you can be a bit brief here as long as you have the key things. So, of course, because it's negative, that means that our height is decreasing at a rate of 8.05 meters per second, right? So we need to have our units here, and the negative simply means it's decreasing. Now we should technically say here between 2 and 2.5 seconds as well, but like I said, you can be brief as long as you have those keywords. Now, just to make sure you really understand this, I want to give you sort of a graphical interpretation of what this means. So just using Desmos, if you can take a second and you can punch that football formula into Desmos. So h of t equals negative 4.9 t squared plus 14t plus 1, and draw a quick little rough sketch. Okay, so the exact points don't really matter. I just want you to get the idea here. So in question A, where we looked at the first second, we looked between time is 0 and time is 1. Okay, so this is the secant line, and the slope of that line we got was negative 1. And you can see from the picture that, of course, the height is increasing at that time because the slope is positive. Now, similarly, on the right-hand side, in B, we looked at between approximately 2 and 2.5. Okay, so this is another secant line here. And we got the AROC, or the slope of the secant line, to be negative 8.05. And again, you can see that, of course, the height is decreasing at this time. Okay, so that's the graphical interpretation of what we mean. Let's take a look at another one. In this next example, we're going to take a look at a graph. So during the 1997 World Championships in Athens, Donovan Bailey, remember I told you about him that he was a runner, ran a 100-meter race. Okay, so this graph and this table show his performance during the 100-meter race. So we can see from both the table and the graph that the average velocity is going to be the change in distance over the change in time. And we can see from the table or the graph that the distance that he traveled is 100. Just put the units there, meters, so that you have it. And he did that in 9.77 seconds. Okay, so his average velocity was 10.2, let's say, meters per second. Okay, so our secant line from 0, 0 to 9.77, 100. And then this line right here, very hard for me to draw a straight line in this particular one, but that is our secant line. Okay, and a reminder that the slope of this line, the slope of this secant line, is equal to the average rate of change. Okay, so the first secant line would be this point, and then we have this middle one right here. And of course, using a ruler, I would draw this lovely secant line. Okay, and the second half would be from here to this final point, and same thing, we would try and draw a line through those 2 points. And even just by looking at these lines, I hope you can see that the green line is steeper than the blue line, right? The slope of the green line is greater than the slope of the blue line, meaning the average rate of change, in this case, the average velocity, should be greater, okay? And I want to prove that to you algebraically, and so we'll take a look on the next slide. Okay, so the first thing we're going to do is calculate his average velocity by simply taking the change in distance over the change in time. So I'm going to go back to the graph to do that. Okay, so just putting it over here so that we have it, it was 10.2 meters per second. Okay, so question B asks us to draw a line from 0, 0 to that final point on the graph. And just a reminder that this line is called a secant line. So I'll go back and do that. Okay, and to find the slope of that line, that secant line, we would take y2 minus y1 over x2 minus x1, and of course we would get the exact same answer, 10.2 meters per second. Okay, so now let's take a look and use this idea of secant lines, and we're going to draw secants from 0, 0 to 5.44, and then we're going to draw a secant for sort of the second half of his race. And what we're going to do is we're going to look at the average velocity, or the average rate of change, between the two different halves of the race and see what happened, okay? So I'm going to try and color code this for you. So I'm going to go back to the graph, and we're going to draw the first secant line. Okay, so the average velocity, which we can say is the average rate of change for the first half. Again, we're just going to use basically our slope formula, our y2 minus our y1 over x2 minus x1. Okay, and when you go ahead and you calculate that, you get approximately 9.2, and again, that's in meters per second. Okay, let's take a look at the second half. Okay, same thing, y2 minus y1 over x2 minus x1. So as you can see, we got 11.5 meters per second, which again shows you that the slope of the green secant line was greater than the slope of the blue secant line, and that tells us that he was faster in the second half of his race. Okay, so that gives you a look at graphically. Let's do one more algebraically. Okay, so we have the cost of making 1 unit of product at any time in years. Modeled by this function, we're going to look at the average rate of change on the interval. Hopefully this makes sense to you, between 5 and 30. And then we're going to look at a graphical interpretation as well. Okay, so very important to understand the setup, right? So the average rate of change, we're going to look at y2, which in this case is c at 30, minus c at 5, over 30 x2 minus x1. Okay, so you need to find C at 30, you need to find C at 5, keep them as exact as possible, so pause the video and try to get the answer by yourself. Okay, so hopefully you got 1,487, double check carefully. Now, let's interpret this and try to get the units because that's one of the most important things here. So the cost is in dollars, so this is dollars on the top if you like, at any time, so it's dollars per year. Okay, so what does this mean? This means that the cost is increasing at a rate of $1,487 per year. Okay, so sentence and units are the most important. Okay, and I want to just take a quick look at this using just graphically again so I can emphasize what this means. So if you can pause the video and quickly punch that into Desmos and get a quick sketch, that would be great. Okay, so we know it's cubic, leading coefficient is negative, and you can get the approximate x-intercepts, which aren't important, from your graphing tool. Okay, but again, we're looking between, 5 and 30, so very close here. Those are our 2 points. This red line I'm drawing would be our secant line, and we know that the slope of the secant line would equal 1,487. And again, you can see that it's positive. That's one of the things that I want you to understand here. Okay, so we are going to continue on now, and we're going to look at not the average rate of change, but we're going to look at the instantaneous rate of change. Same thing, we're going to sort of look at it graphically and algebraically, and we're going to see the difference between the two. Okay, so here we have a physics teacher that wanted to demonstrate the effects of gravity. Sorry, a bit of that got cut off. So he dropped a weight from a known height and measured its position. So we have a position, time graph, position in centimeters, time in seconds. And we know that if we were determining the average speed, the average rate of change of the weight between 0.2 and 0.4 seconds, we know that that would look like this, right? We would look at 0.2, we would look at 0.4, we would draw a line through those points. We don't have a function here, right? So we know that that would be the secant line. And we would know that whatever the slope of the secant line is, that would equal this average rate of change or this average speed. Okay, so now the new question is, what if I asked you to determine the speed just at 0.3 seconds? Okay, so just at 0.3 seconds, that is called the instantaneous rate of change, right? The rate of change at one specific point, okay? And there, what we would draw is what's called a tangent line. So we would draw a line that only touches the curve at that one spot. And it's very hard to do that accurately using a graph. Sorry, again, that needs to be a straight line, but you get the idea. And it would be a line that only touches the curve at that point, and that is called a tangent line. And then if we found the slope of that line, okay, that would represent the instantaneous rate of change. So that would be the slope of the tangent line. And I'm not going to actually do that graphically because, like I said, it's very hard to draw an accurate line and find the slope of it on a grid like this. So we're going to focus definitely more on algebraically, but I want you to understand what a tangent line is when we draw it. Okay, so please take a look at some of these notes, okay? So first of all, the instantaneous rate of change, or the IROC as we call it, is the rate of change at a specific point. In this case, it would be the speed of the weight at the instant 0.3 seconds, as we said. The IROC corresponds to the slope of the tangent line, so we're going to want to highlight that, okay? The IROC is the slope of the tangent line at exactly that one specific point. And so the idea with drawing that tangent line is it intersects the curve at just that one point. Okay, graphically, if I was to ask you to do that, we would draw the tangent line and we would have to find 2 points on that line and find the slope between those 2 points. We are not going to do that graphically, but that would be the idea. Okay, so we're going to move more to the algebraic approach of how we would find this instantaneous rate of change because we only have 1 point. Okay, so to do this, we're going to take a look at this scenario. City engineers estimate that the accumulation of solid waste, note it's in hundreds of tons, might just want to make a note about that, hundreds of tons at the city landfill, can be modeled by this equation. okay, where T is the number of years since 1990. So to get us going on this question, I want us to determine just the average rate of change between 2 points between the year 2000 and 2005. One thing to note on this is it's just being tricky, right? Since this function is defined where T is the number of years since 1990, this would really mean between T equals 10 and between T equals 15. Okay, so a reminder when we're setting up our AROC, right? It's going to be y2 or f at x2. So in this case, w, the function is w at 15 minus w at 10 all over 15 minus 10. So you want to make sure that you've got that set up and you know how to get that exactly. Okay, and same thing as always, pause the video, see if you can get all those values by yourself here. So just rounding our final answer, you should get 448.0. Rounding to 1 decimal place is great. Okay, and again, I want you to pause the video, see if you can get the sentence by yourself with the units. Okay, so we have the amount of waste is increasing, right, because it's positive, at a rate of 448 tons, right? 100 tons per year. Now, you could also write this as 44,800, and you could just say tons per year, and that would be okay as well. Up to you how you want to express that. Okay, so that's a recap of what we've been doing before. Now let's see what we're going to do a little different. Ultimately, the question we're going to try to tackle is the instantaneous rate of change in the cost in the year 2000, and don't forget that that is T equals 10. Okay, so what we're going to do is we're going to do the average rate of change, and we're going to make the interval, as you can see, get smaller and smaller and smaller as we move down this table. So we actually did the first one between 10 and 15 already, right? And we found out that the AROC was approximately 448, right? 0.0 was the value we got. You want to keep as many decimal points as possible. Okay, so now I want you to repeat this process for the AROC between 10 and 11. Okay, so I'll just set you up to make sure you got this idea. Remember, that would be W at 11 minus W at 10, which note you already have that value, so use it, over 11 minus 10. Okay, so the only new value you really need to figure out is W at 11, right? And then the rest of the math is easy. You show as much work as you want in this table to get your final answer, and you can round your final answer to 1 decimal place, or if you want to keep a few extra along the way, that's always a good thing. So when you're calculating W11 or whatever the first value is, it's good if you can keep a lot of decimal places as you move on. Okay, so go ahead, pause the video and see if you can do that. Okay, so for my value there, I got 1,419.6. minus 1104, we already have that, that's all over 1. And so I got approximately 315.6. Okay, so I want you to continue finding the average rate of change. Note the intervals are getting smaller and smaller and smaller, okay? So you're going to need to pause the video and complete as much of this table as you can on your own. Okay, so take a look. I stopped showing my work a little bit at the end there, but you can see that as the intervals get smaller and smaller and smaller, you start to see that the numbers sort of plateau, I guess you could say, at 287 approximately. There's a 0.00 whatever on the end there, but that really is your conclusion, okay? So what we can say really is, therefore, in the year 2000, T equals 10, right? The amount of waste is increasing at a rate of 287 tons, or 100 like that, tons per year. Okay, and so what I want you to see here, first of all, is that finding the instantaneous rate of change is an estimate. Okay, we are estimating the instantaneous rate of change by using a very small interval surrounding the point. And what I'm now telling you based on what we've seen is this final calculation here is sufficient. We don't need to go through the whole table to prove it. Basically what I'm saying is 0.001 on either side of 10, let's say, is close enough. So all we really have to do to find the instantaneous rate of change is this last one. Now, if we're finding the instantaneous rate of change at 10, 9.999, between 9.999 and 10 would also give you the exact same answer. Okay? So I hope that I've shown you that basically by choosing a really, really small interval, we're taking the average rate of change and basically calling it the instantaneous rate of change, or estimating the instantaneous rate of change. So let me show you quickly what a question would look like. Okay, so we'll start with a really simple function, just still a quadratic, but the same concept applies to all polynomials and all functions, really. So the height of a rocket is modeled by this equation. Okay, now the question would say determine the rocket's velocity or determine the rocket's instantaneous rate of change at exactly t equals 4 seconds. Okay, so what we would write is fairly similar, except it's IROC. And the one thing I want to emphasize here is it's an approximation. So you need to show that it's an approximation every single time. Okay, same concept. We're going to use the average rate of change on a really small interval. So we're going to use the interval between 4 and 4.001, or similarly, you could use 3.999 and 4. So your choice. Okay, so you could use 4. Okay, I usually like the 0.001, but it doesn't matter. Okay, so using our formula for average rate of change, we're going to find h at 4.001, subtract h at 4, all over x2 minus x1. Okay, so pause the video. Let's try to get an answer for that. The only thing that I'm going to tell you that's really, really important just in setting this up, okay, you'll end up with 0.001 on the bottom. H at 4 will be a nice number. But H at 4.001, please make sure you are keeping a lot of decimals. I usually just write in everything in my calculator or do it all in one step. Okay? You can do the work off to the side of your page if you want, or you can just write down the numbers and keep lots of decimals. Okay, so I got 23.5857951. Like I said, keep lots. I usually just keep everything I can see. And when I punch that all into my calculator, you may round your final answer to one decimal place. I got negative 14.2. Okay, so now pause the video for a minute and see if you can interpret what that means in your sentence. Okay, so at 4 seconds, the height of the rocket is decreasing, right, because it's negative, at a rate of 14.2. Units here are easy. Units of height are meters. Units of time are seconds. So at a rate of 14.2 meters per second. Okay, so you're going to need to practice some of this. Good luck.